Hello everyone, welcome back you all in this new video where we are going to see manual approach for design of your combined foundation. This complete problem we are going to solve in 5 important steps. In the first step we will see the problem statement along with the brief general discussion about the combined foundation design. In the second step we will see how to decide in-plan dimension of the footing as length, width and depth. In the third step we will see design for the reinforcement along the length and width of the footing. In the fourth step, there will be design checks against the one-way and two-way shear. And in the last step, we will see the final design schedule and detail of this footing. First of all, try to understand the problem statement. Two columns having the cross section as 250 by 250 mm and 300 by 300 mm. They are subjected to a load of 300 kN and 500 kN respectively. The center to center distance between these two columns are 4 meter. The bearing capacity of the soil at the proposed land is 100 kN per meter square. We have to design a rectangular combined footing being width as 1.5 meter. We have to use the grade of materials as M20 and Fe415 for the concrete and steel respectively. So with all of this given data, we have to design the combined foundation. Let's start the design. In the first step, we need to find out the in-plan dimension of your footing as length of the footing and width of the footing. So to find out the length of the footing and width of the footing, we need to know the how much the load is going to be transferred to your subsoil. So the load coming from your column is not only the load which is going to be transferred to your subsoil, but also there is an addition of self weight of your foundation. So the load coming from your column plus self weight of the footing will combinedly is going to be transferred to your subsoil. So we need to do the calculation for that. So the total load coming from your column is going to become 300 plus 500. It is going to become totally as 800 kilonewton. Now we have to consider the self weight of the footing. So to calculate the self weight of the footing, we need to know the length of the footing. We need to know the width of the footing. So without of the design, how you can come to know the how much the length of the footing and how much the width of the footing, and also we should know the depth of the foundation for knowing the self weight of the foundation slab. That's why we need to do the assumption as self weight of the footing is 10% of the load coming from your column. So that is going to become what? 80 kilonewton. So if you are going to add these two values, so you are getting the what? Total load which is going to be transferred to your subsoil as 800 plus 80, 880 kilonewton. Now I want to calculate the in-plan size of your footing as length and width. Or in another way, you can say that how much the area of footing required. So the area of footing required is equal to your total load that is going to be transferred to your subsoil divided by SBC of the soil. So in our problem statement, we have given that the SBC of the soil is 100 kN per meter square. So if you are going to take the ratio of total load which is going to be transferred to your subsoil divided by SBC of the soil, so you will get the area of footing required as 8.8 meter square. But one more important thing here, it is given what? While designing of this combined foundation, we have some limit. That limit is what? Width of the footing you cannot take more than of 1.5 meter. So for that, here I am going to say limiting width of the footing as 1.5 meter. So area of footing is equal to length of the footing multiplied by width of the footing. Now width of the footing is what? Fixed. Length of the footing, width of the footing is what? 1.5 meter, and total area of footing required is what? 8.8 meter square. So just take the ratio of this length of the footing will equal to 8.8 divided by 1.5. So you will get the length of the footing required as 5.86. So this much the length of the footing is required. So I am going to consider slightly more value than that of this requirement. So I am going to consider the length of the footing as 6 meter. So finally the width of the footing and length of the footing is going to become 1.5 and 6 meter respectively. Now finally the area of combined foundation provided is going to become length of the footing multiplied by width of the footing as 1.5 multiplied by 6. It is going to become 9 meter square. So area of footing required was 8.8 meter square. Area of footing provided is going to become what? 9 meter, means area provided is greater than area required. So we are going to say that the provision is what? Safe. After finalization of length and width of the footing, we have to position our foundation under the column, and for that we have to understand some important thing. So for that, have a look over this drawing. So here we have to put our foundation under these two columns, but there is a recommendation that the pressure distribution at the base of the footing should be uniform. It means that at this edge the pressure intensity should be same as that of the pressure intensity at this edge. But this is only possible when if the two loadings are there and the CG of the loading and the CG of your foundation area, if it is going to be coincide, then only we are going to ensure that the pressure distribution at the base of the foundation will be what? Uniform. So for that we have to do some calculation to decide that your CG of the loading and CG of the footing are going to be coincide. There only you can ensure that also the settlement under the foundation will be uniform. Pressure will also be uniform and settlement will also be uniform. If you are coinciding the CG of the loading and CG of the footing, but if you are failing to maintain the CG of the loading and CG of the footing at the same point, what will happen? The pressure distribution will not be uniform. One side there will be less pressure distribution, at the other side there will be the more pressure distribution. And with this difference of this pressure distribution, what will be there? There will be unequal settlement in your foundation. Somewhere there will be lifting of the foundation, somewhere there will be the settlement of the foundation. That's why when you are going to design the combined foundation, it is very important to ensure that the CG of the loading and CG of the footings are going to be coincide. Have a look over this note. The same thing is given here. To have the uniform pressure distribution, the CG of the load should coincide with the CG of your footing. For that, let's consider the CG of the load is at a distance of x from the center of the left column. So here in the figure you can understand the CG of your load is at a distance of x from the center of your left column. And if you want to calculate this x value, so what you need to do, you have to multiply the load that is coming over this second column 500 kilonewton by the center to center distance as 4 meter. So 500 multiplied by 4 divided by the intensity of the loading coming to this column plus the intensity of the loading coming through this column. It is going to become 300 plus 300. Totally it is what? 800. If you are going to take the ratio of these two, you will get the value of x is equal to 2.5 meter. So the projection from the center up to the CG of your loading is how much? 2.5 meter. Now what I want to do, I am going to say that this CG is actually not the CG of your load, it is also the CG of your area, and or in other way I can call it as it is the midpoint of the length of your footing. So it is going to become L by 2 and this much is going to become L by 2. So is the total length of the footing divided by 2, total length of the footing divided by 2. So if I want to calculate the projection from the C1 column up to the edge of the footing, so I am going to call it as what? A. How I can calculate this? This is the length of the footing divided by 2 minus x. You will get the value of A. So here the same thing I am going to do. So A is equal to length of the footing divided by 2 minus 2.5. So you will get the value of 0.5 meter. As your length of the footing is 6 meter, divided by 2 minus this x value. So you will get the value of projection up to the edge from the center of your column C1 as 0.5 meter. In the same manner, you have to do the calculation for this side. So we know that this is the 4 meter and it is what? 2.5 meter. If you subtract this 2.5 meter from this 4 meter, you will get the remaining value here. And now if you subtract this remaining value, that is what? Your 4 meter minus 2.5 meter. If you subtract this complete value from the LF by 2, you will get this remaining portion that I am going to call it as what? B. So to calculate the B value, same formula I am going to apply here. Let me show you. Here the value of B is going to become L by 2 minus 4 minus 2.5. After taking all that values, we are getting the value as 1.5 meter and A value we are getting as 0.5 meter. Now net upward soil pressure at the base of your foundation, it is going to become total intensity of the loading coming from both of the column divided by provided area
of your footing, that is 9 meter square. So we are getting the upward soil pressure as 88.89 kilonewton per meter square. So with this net upward soil pressure, we have to do the further calculation.
After all of this calculation, we are having the result that the length of the footing as 6 meter with a break of 0.5 meter from the edge of the footing up to the column number 1 at its center as 0.5 meter, and from column C1 to the column C2 center to center distance as we have given as 4 meter, and from the column number C2 center to up to the edge of the footing the span is what, 1.5 meter, and this foundation is subjected to the upward soil pressure as a uniform upward soil pressure as 88.89 kilonewton per meter square. So with all of these results we have to proceed for the further design. Now next we have to find out the shear force and bending moment along the length of your foundation. And to calculate the shear force and bending moment at different points along the length of your foundation, I need to have the upward soil pressure in kilonewton per running meter by considering the full width of your foundation. Just try to understand, as our foundation is having the size as length as 6 meter and width as 1.5 meter, and for that we are having the upward soil pressure as 88.89 kilonewton per meter square. So I just want to calculate the shear force at this point, shear force at this point, shear force at this point, and shear force at this point. Likewise, I want to calculate the moment at all of these points. So for that I need to have this pressure in kilonewton per running meter by considering the full width of your foundation. So I have to multiply this value as 88.89 kilonewton per meter square multiplied by total width of your foundation is going to become 1.5 meter. If you are going to calculate this value, so you are getting the answer as 133.335 kilonewton per running meter. So with this value you can calculate the shear force at all these different points as well as the bending moment at all these different points. So in later step we have to do the same thing as of calculating the shear force and bending moment. So first of all I am going to calculate the shear force at this first point. So at this first point how much shear force will be there? So at every point we have to consider the two sections. One is on left hand side, one is right side of that considered point. So on the left hand side, as you can see, nothing is there. So that's why shear force at this A point will be 0. When you come to right side of this point, again no loading is there. That's why shear force finally at this particular point will be 0. So that is what actually given here. Shear force at the point A is actually 0. Now when you come to this B point, I am going to call it as what? It is the B point. So at this B point for the column C1 center, I am going to call it as B point. So at B point I am going to consider two sections. One is on left hand side, one is on right hand side. So on left hand side there what? This full span you have to consider. And upward soil pressure is what? In kilonewton per running meter length, it is 133.335. That is what actually given here. 133.34 here it is what considered, multiplied by this span 0.5. If you are going to multiply this value, you are getting the shear force at that B point at left as 66.67 kilonewton. On right hand side, when you come to this right hand side, what will be there? This load also you have to include. So upward shear force is what? 66.67 kilonewton, and downward is how much? 300 kilonewton. So what value here it is going to become? 66.67 positive minus 300, it is going to become minus value downward side 233.33 kilonewton. So that is what the value in respect of your B point. Now directly I am coming to this point. Now next we have to find out the shear force at the center point under the column C2, and for that I am going to consider two sections. One is on left hand side, one is on right hand side of the center point. But when you are going to do the calculation for the left hand section, we have already the value at this center point, that is what your B. So here the downward value we are having, resultant downward value for the B point as 233.33 kilonewton. So if you are going to calculate at this left hand point, so this is already downward value we are having how much? 233.33 kilonewton, which is in downward direction. Now this much span we have to consider, that is what? 4 meter,
and the upward soil pressure in uniformly distributed form, that is what 133.34 kilonewton per meter. So I am going to multiply this value with this center to center distance as 4 meter, and I have to add this value as downward 233.33 kilonewton. So you are getting the resultant value for the left hand side for this C point, which is at the center of your column C2. So same calculation I am going to do here. For the C point left hand, minus value is 233.33 plus 133.34 multiplied by 4 meter. So you are getting the resultant value for the C point for the left section as 300 kilonewton, and this is what it is, the positive value. It is in upward direction. Similarly, you have to do the calculation for the right hand side section from this center point, but for that we are having the resultant value for this left hand, that is what positive 300. Now it is going to become downward 300, that is what downward 500, which is in minus value. So I am going to put here positive 300 and negative 500. Resultant value of the shear force you are getting as 200 kilonewton, right? So for the C point left hand, for the C point right hand, likewise you have to come to the D point. I am going to call this end point as a D point. So for the D point, left hand section, right hand section. So when you come to the left hand section, so already we are having the resultant value here as what, downward as 200 kilonewton resultant value for this C point, but you have to add this value with this upward soil pressure in kilonewton per running meter as 133.34 kilonewton multiplied by this much span. So it is going to become 1.5. So with this calculation we are getting the resultant value as here 0 kilonewton. So at D point 0 shear force, at A point 0 shear force. In between we are having the different values of the shear force. So as per these all resultant values of the shear force at different points, we are going to draw the shear force diagram. So here I am going to draw the shear force diagram. So at A point shear force is what, 0. At B point two values are there. One is positive value at 66.67, and at B negative value is there what, 233.33 kilonewton. Likewise for the C point, left hand side positive value is there and right hand side negative value is there, and at D point the value of the shear force is what, 0. So in this way you have to do the calculation for the shear force, and accordingly you have to prepare the shear force diagram. After that, one more thing, that is the most important thing, you need to know the point of zero shear force distance. At what distance this point of zero shear force is available from the center of this C1 point. At what distance this zero shear force is available. Here it is what, negative value, here it is what, positive value. Negative and positive. In between, when the sign is going to be changed from negative to positive, you are having the point of zero shear force. So I want to know this distance from the center of this C1. Why it is needed to know the distance of this point? Because at this zero shear force we will get the maximum bending moment. That's why it is important to calculate the distance of this point. Okay, so how to do the calculation for to know the distance of this point? So you need to go with the symmetry of the triangle. So I am going to say that this point is at a distance of x1 from the center of this column C1. This point is available at a distance of x1, and this remaining portion is going to become what, 4 minus this x1. Very simple. So with all of this I am going to do the calculation here. This is what, 300 divided by this side, 300 divided by 4 minus x1 that I have written here is equal to what, this value 233 divided by this x1 that I am going to write here. Okay, thereafter cross multiplication will be there. Then you have to solve these equations. You will get finally the value of x1 as 1.75 meter from the center of this column C1. The point of zero shear force is what, at a distance of 1.75 meter. Okay, but we know this from the center of this C1 up to the edge of the footing, how much the span is, that is what, 0.5 meter. So if you are going to add this 0.5 plus 1.75, so you are getting the final point of zero shear force distance from the edge of the footing. It is totally how much? It is 2.25 meter. Right. So in this way we have to do the complete calculation for the shear force, and the shear force diagram you have to draw accordingly. Thereafter you have to find out the bending moment at all these different points. Okay, so I want to calculate the bending moment at this point, edge point. Then I have to calculate the bending moment at the center of this column C1. Then I have to calculate the bending moment at the center of the column C2. Then I have to calculate the bending moment at the edge of this footing. So you know that at the edge of the footing, the bending moment will be what? 0. At this edge of the footing, bending moment will be what? 0. So at both of the ends of the footing, the bending moment will be 0. Then your responsibility is to calculate the bending moment only at the center point. Here I have to calculate the bending moment. Here it is my B point. Here it is my C point. Here it is my D point, and here is my A point. So at A point bending moment is 0. At D point bending moment is 0. Now I have to calculate only the bending moment at this B point. I have to calculate the bending moment at this C point. For these 2 points only I have to calculate the bending moment. So if you are going to do the calculation, so either you have to consider the right part for the calculation of bending moment at this center point, or you have to consider the left part. We are having the uniformly distributed upward soil pressure, that is what, 133.34 kilonewton per running meter, by considering the full width of the footing. I have explained this earlier in detail. Okay, so this is in kilonewton. So I have to multiply for this cantilever portion, this projected part. So it is going to become 133.34 multiplied by, this span is what, 0.5 meter square divided by 2. This is the formula to calculate the bending moment at this center point under the column C1. Similarly, if you are going to do the calculation for this center point under the column of your C2. So how to do the calculation? Again, 133.34 multiplied by, it is going to become what, 1.5 square divided by 2. If you are going to do the calculation with these values, so you are getting the calculated value for the bending moment at A is 0. For the bending moment at B, the formula is what, 133.34 multiplied by 0.5 square divided by 2. You are getting the bending moment as positive. Here it is what, suppose this is the point, I am going to calculate the bending moment here, and upward pressure is like this. Okay, so it is what, clockwise. So I am going to consider it is at what, positive bending moment. So here positive bending moment 16.667 kilonewton meter. Likewise at the C point, this is your A, this is your B, this is your C under the column, and now this is your D. So at A and D bending moments are 0. At B we have calculated the bending moment at 16.667 kilonewton meter. Now come to calculate at the C point. So at the C point bending moment is what, 133.34 kilonewton per meter multiplied by 1.5. This much span is what, 1.5. You are square divided by 2. You are getting the bending moment as 150 kilonewton meter. Okay, now next, that is what, you have to find out the bending moment at this zero shear force point. So how you can calculate at this point? So it is very simple. Okay, that is what, total upward soil pressure, that is what, 133.34 kilonewton per running meter multiplied by this total span is how much? From the edge we have calculated as 2.25. So it is going to become 133.34 multiplied by 2.25 square divided by 2. This is what, clockwise. Now here the downward force is available, that is coming from your column, is what, 300 kilonewton. So this 300, it is what, anti-clock. So this 300 and this distance is how much? This is 1.75. So you have to subtract this value. So resultant value of the bending moment you are getting as negative as 187.49. It means that it is the hogging moment, and these two moments are your sagging moment.
These two moments are positive moments, that's why I'm going to call it as sagging moment, and this negative moment you are getting, it means that it is the hogging moment. Okay, so based on this bending moment values, I'm going to draw the bending moment diagram. So under the column C1 you are getting the positive bending moment, so is a positive bending moment, sagging is there. Here you are getting the positive bending moment under the column C2, so it is 150 kilonewton service bending moment, and here it is what negative bending moment you are getting as, so it is what negative, and below this line it is positive, and above this line it is what negative. So negative values of the bending moment is what 187.49 kilonewton meter. So here it is what we had to find out the how much effective depth is required to resist this deformation of your footing. So under the application of the loading, your foundation is going to be deformed and these movements are going to be generated. To resist this much movement, how much the effective depth of the footing is required or total depth of the footing is required, that I want to calculate. So amongst all these three values of the bending moment, we have to consider the maximum one, irrespective of the sign. It doesn't matter whether it is positive or negative, irrespective of the sign or irrespective of the nature of the movement, whether it is positive or negative, we have to consider only the number. So based on number, which one is the maximum value? Obviously the maximum value is what 187.49 kilonewton meter. So based on this maximum bending moment, I have to find out the how much effective depth or how much the overall depth of the footing is required to resist the deformation or to maintain its stability under the flexural behavior. What does mean by flexural behavior? I will explain it later. So here it is what maximum bending moment to find out the effective depth and overall depth requirement. So it is going to become 187.49 kilonewton meter. So value here we are going to consider multiplied by 1.5 because all these values are service values. We have to find out the ultimate value or factored value, so you have to multiply this value by 1.5. so finally you are getting the ultimate moment as 281.235 kilonewton meter. So the formula for finding out the effective depth, it is what ultimate moment is equal to 0.138 FCK BD square. So if you want to calculate the effective depth, so that is going to become effective depth will equal to square root of mu ultimate moment divided by 0.138 FCK B. So put all the values here. So 281.235 into 10 raised to 6 in Newton mm divided by 0.138 FCK is characteristic strength of your concrete is 20 multiplied by width of your footing. So total width of your footing is what? We are doing the calculation along the length. This is what along the length, and for that how much the total width is, that is what 1.5 meter. So it is going to become 1500 mm. So 1500 mm you have to put here. So it is asking to provide as 260.64 mm as effective depth of your foundation is required to resist this much maximum movement 187.49 kilonewton meter. So to resist that much movement, we need to provide at least 260.64 mm. But for the safety concern, I am going to provide the overall depth as 450 mm directly. Demand is what 260, I am going to provide overall as 450 mm as overall depth. So you may raise a question that why you are going to consider this much overall depth where demand is what only 260. So the answer is what, or explanation is what? See, your depth of the foundation is going to be required by two criteria. One is your flexural criteria, another one is your shear criteria. So based on flexural requirement, this much effective depth of the footing will be enough. But if you are going to check this effective depth, or in respect of this you are going to check your depth under the shear requirement, so this may get fail because the depth of the footing requirement is based on your shear requirement mainly. That's why we are going to provide the overall depth as 400 mm for the complete footing. Okay, so here we are going to consider the clear cover as 50 mm and the diameter of bar as 16 mm. With all of that, the available effective depth will become as 450 minus clear cover as 50 mm minus half of your diameter of bar. Overall you are getting available effective depth as 392 mm. Okay, so effective depth required is 260.64 mm and we are going to provide the effective depth as 392 mm. So provided depth of footing, effective depth of the footing is 392 mm, which is greater than that of your depth required, that is what, 260.64 mm. So we can say that our design is what, safe under the flexure.
Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program, you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real life project, we will cover the raft foundation. And in the fourth real life project, there will be the coverage of pile and pile cap design of basement wall. And at the end of this training program, we will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by experts. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now, more than 1,000 participants have benefited from this training program. Now you are the next.
Now after deciding the overall depth of foundation as 450 mm, or in another way you can say that the effective depth as 392 mm, based on the flexural requirement or flexural criteria, we have to check this project depth against the punching shear check as per your IS 456-2000. So for that, we have to consider the critical section at a distance of d/2 from the face of your column. But the problem here it is what? We are having the two columns, one is as C1, another one is C2. Both of the columns carrying the different intensity of the loading. Your C1 is carrying the intensity of the loading as 300 kilonewton and your column C2 is carrying the intensity of the loading as 500 kilonewton. Okay, so one is light loaded column, another one is the heavily loaded column. So here we are going to perform the check under the C2 column. Why it is? Because it is heavily loaded column. It is subjected to high intensity of the loading. So if your footing is coming out to be safe under the punching shear check under the column C2, which is heavily loaded, so it's obvious that your depth will be safe under the C1 column also. That's why we are going to perform the check under the heavily loaded column as C2. So I am going to consider a critical section at a distance of d/2 from the face of your column. Here it is what, d/2 from the face of your column. Here d/2 from the face of your column, and here it is d/2 from the face of your column. So in all of the direction I am going to consider my critical section at a distance of d/2 from face of my column. So here actually what we need to do, we have to find out the nominal shear stress at this critical section. The formula is what? Shear force at this critical section, ultimate shear divided by perimeter multiplied by your depth of the foundation, effective depth. This will be what? Your nominal shear. And as per your IS 456-2000, you have to find out the critical shear at this section. And you have to compare this nominal shear and critical shear. If you are getting your nominal shear less than of your critical shear, we are going to say that our depth is okay under the punching shear. But in a situation when you are getting the nominal shear more than that of your critical shear, then there is a problem in your design. You have to increase the depth of the foundation to make it safe under the punching shear check. Okay, so what next step is what? We need to find out the how much the shear force is going to be developed at this critical section. Now we have to find out the shear force at this critical section, and the formula for finding out the shear force at this critical section will equal to 500 the load were carried by this column C2 minus this upward soil pressure multiplied by with the area of this punching shear section. And the formula for calculating the area of this punching shear section is what? 0.3 plus D. D is what? d/2 from this side, d/2 from this side. It is going to become D. So 0.3 is side of your column and half, it is going to become complete D. So it is totally becoming what? 0.3 plus D. So how much it will be? 0.3 plus 0.392 is actually the effective depth of your foundation. If I am going to multiply this side with this side, again the same dimension will be 0.3 plus 0.392. It is going to become square. So the same thing is actually present here. After the calculation, you are getting the shear force as 457.433 kilonewton. So it is what service shear force. I want to calculate the factored shear force. So you have to multiply this value with 1.5. You are getting the factored shear force as 686.15 kilonewton. So the shear force we are getting. Thereafter, I have to calculate the perimeter length of this punching shear section. And how you can calculate that? So you have to multiply this each side with 4 times. So it is going to become perimeter length of shear area. I am going to represent it by B dash 4 times this one side. So it is what 0.3 plus effective depth. So in mm it is going to become 300 plus effective depth is 392 and 4 sides are there. If you are going to multiply it with 4 sides, you are getting total perimeter as 2768 in mm. Thereafter, in simple you have to calculate the nominal shear force at this critical section. How much nominal shear force is going to be developed? The formula will equal to VU ultimate shear force divided by perimeter multiplied by effective depth. With all of this value, you are getting the nominal shear at this critical section as 0.6323 MPa Newton per mm square. Thereafter, I have to calculate how much the critical capacity of this punching shear section. So shear capacity will equal to tau c into Ks, where Ks is equal to 0.5 plus beta c, where beta c is equal to shorter side of the column divided by longer side of your column. So here our column is what 300 by 300 section size. So it is going to become 1. So if you are going to put the value here as 1, so total Ks value you are getting 1.5. But if you are going to look IS 456 2000 page number 58 clause number 31.6.3, there you will get this Ks value you cannot use beyond the 1. Maximum value you can use as 1. So here we are getting the Ks value more than of 1. That's why we are going to limit it to maximum of 1. Now put this Ks value in this shear at critical section. So Ks is equal to 1. So ultimately you are getting shear at critical section as tau c. Now the formula for finding out the tau c is equal to 0.25 under root of FCK. Your characteristic strength of concrete is what 20. So 0.25 under root of FCK, you are getting the value of tau c as 1.118 MPa Newton per mm square. So this is called as what? Nominal shear. This is your critical shear, and you have to compare these two shear stresses. So we are getting the nominal shear is less than of your critical shear. Hence that we are going to decide our provided depth is safe in punching shear. In next step, we have to find out the reinforcement in your combined foundation slab. For that, we need to understand some important things. So here we have to provide the reinforcement in your combined foundation slab along the length of the foundation at its top and bottom face, as well as the reinforcement along the width of the foundation at its top and bottom face. So to decide the reinforcement along the length of the foundation, when it will be at the bottom, when it will be at the top, for that we need to understand the bending moment diagram. So here your bending moment diagram is present. After the analysis, we are getting the bending moment under the column C1 as 16.667 kilonewton meter, and under the column C2 we are getting the value of moment as 150 kilonewton meter. So these two values are positive moments, and here in between of this C1 and C2 we are getting the bending moment as 187.49 kilonewton meter. So this is actually the negative moment. So this bending moment diagram is very important to understand the position of the reinforcement. Thereafter, the second diagram is your flexural behavior of your foundation under the application of the loading. So with this flexural behavior of your foundation under the application of the loading, you can decide the positions of the reinforcement. So here you can understand that under the column loading, this part of the foundation will be under compression. It is going to be deformed like this. And here under the column C1, your foundation slab is going to be deformed in this direction, because under the application of the loading, there will be what? Upward soil pressure, we know very well. So here under the column, the downward pressure will be dominating in respect of your upward soil pressure. That's why there will be what? Deformation. So there you will get the tension at the bottom face of your foundation. Here under this C1 column, again the downward pressure will be what? Dominating. That's why we are having the tension phase at the bottom side, because it is what? Under the compression. It is going to be deformed like this. So bottom phase will be under tension and top phase under the compression. But when you come in between of this C1 and C2, for this mid portion, what will happen? There is no downward intensity of the pressure. There is no downward pressure. What is there? There is the upward soil pressure. That is what dominating. So it is trying to lift. So with this lifting, what will happen? This portion will be under the compression and this portion will be under what? Tension. So wherever you are getting the tension phase, there you need to provide the flexural or tensile reinforcement or main reinforcement. So for the combined foundation, we need to provide the reinforcement here. Main reinforcement is needed to provide here. Main reinforcement is needed to provide here. Main reinforcement for the top portion we have to provide here. So with this flexural behavior, you can decide the positions of the reinforcement that I have shown in clear way in this figure. So you can understand here the tension is, that's why reinforcement is present here. Here the tension is, that's why reinforcement is present here, and in between of this C1 and C2 the tension is at the top face. That's why we need to provide the tensile reinforcement along the length of the foundation at top face. So these all are the main reinforcement, but here in between this you have to provide the minimum reinforcement bottom. Beyond of this you need to provide the minimum reinforcement here. You need to provide the minimum reinforcement here. Why? It is because there is a compression, so no design reinforcements are required, but there should be some provision of reinforcement as minimum reinforcement. That's why we are going to extend minimum reinforcement beyond this design reinforcement phase. Hope that you all understood. So we have to find out the how much reinforcement required in between of this C1 and C2 column at the top face, how much reinforcement required under the C1 column, under the C2 column for the bottom face. So same calculation we are going to do in our problem. So here reinforcement along the length of the footing. So longitudinal tensile reinforcement for the mid span, that will be obviously at the top. Okay, so here we are getting the moment. How much? Here moment we are getting 187.49. It is what? Negative moment, hogging moment, and wherever you are getting the hogging moment means reinforcement will be at the top. So it is 187.49 kilonewton meter is a service bending moment. I am going to multiply this value with 1.5. That's why I am getting the factored bending moment as 281.25 kilonewton meter. It is the hogging bending moment. That's why we need to provide the reinforcement at the top of the footing. So here ST will equal to 0.5 FCK divided by F5 inside bracket 1 minus square root of 1 minus 4.6 ultimate moment that we have calculated here divided by characteristic strength of your concrete considered width of the footing. So while calculating the moment along the length of the foundation, what we have considered the full width of the footing, that is actually 1.5 meter. So 1.5 meter is going to become what? 1500 mm that I have considered. Thereafter width of the footing multiplied by effective depth is 392. So after taking all these values in this equation, we are getting the area of steel required as 2151.54 mm square as a design requirement. Based on whatever the moment you are getting, accordingly we have calculated this reinforcement. That's why I'm going to call it as what? Design requirement. I have to compare this design requirement with your minimum requirement. Minimum requirement as per the IS 456-2000 for the foundation slab as 0.12% of B into D. So with all of this calculation we are getting as 810 mm square as minimum requirement. You have to compare your design requirement with the minimum requirement. Which one is the maximum one? So we are getting the maximum one as 2151.54 mm square. So we are going to provide this reinforcement. So here I have decided to provide as 16 mm dia. So unit area is going to become 201.06 mm square. So how much spacing is required over the width? What does it mean by this over width? So try to understand. We are going to provide the reinforcement along the length at top face. So its distribution will be along the width. So we have to consider this width. Okay. So with all of this, see here what I need to do. Spacing required unit area divided by total area of the reinforcement required multiplied by full width considered. So 140.132 mm spacing is required. So you are not allowed to provide the spacing beyond of this value. This is the maximum limit. You have to provide the value less than of this. So I am going to round down this value by 25 mm. So it is going to become what? Spacing as 125 mm center to center. So I am going to provide here as 16 mm dia at a spacing of 125 mm center to center along the length of the footing over the width. Okay. So area of steel provided finally is going to become 201 divided by provided spacing of the reinforcement multiplied by full width. So finally area of reinforcement provided is going to become what? 2412.72 mm square. So I want to know how much percentage of reinforcement is provided based on the section size of the footing. So it is going to become what? Total area of reinforcement provided divided by 1500 multiplied by overall depth. So you are getting the percentage of reinforcement as 0.36% and minimum requirement is what? 0.12%. So we have provided the reinforcement more than of the minimum reinforcement requirement, means we are on safer side. So with this, which reinforcement we are getting? We are getting this reinforcement. Have a look over this. So we have decided the reinforcement that we have to provide in between of this C1 and C2 column at the top face of the foundation. It will be what? 16 mm dia at a spacing of 125 mm center to center. Now I have to find out the reinforcement under the column C1. I have to find out the reinforcement under the column C2. For that I have to go to this calculation, and here longitudinal tensile reinforcement under the column C1, and obviously where it will be at bottom. So at bottom, just go to design calculation here. So moment what we are getting? 16.67 kilonewton meter multiplied with 1.5, you are getting the factor value. It is the sagging moment. That's why reinforcement will be at the bottom side. Here same formula is there. You have to put all the respective values here. With all of this calculation, you are getting the area of reinforcement required as 177.84 mm square only, minimum design requirement. Now minimum requirement is how much? 810 mm square. So compare design requirement and minimum requirement, and amongst these two values we have to consider the maximum one. So maximum one is what? 810 mm square. So I am going to provide here as for the bottom face, because it is the minimum area reinforcement. That's why I am going to provide 12 mm diameter of bar with a unit area as 113.09 mm square. So how much spacing is required? Spacing required will equal to 113.06 divided by 810 over the full width multiplied by, so we are getting the result as 209.44. So lower this value by 25 mm factor. So I am getting the finally provided spacing as 200 mm center to center. So here I am going to provide 12 mm diameter of bar at a spacing of 200 mm center to center along the length of the footing at the bottom face. So here I am getting the value. Just go to this, and here it is actually 12 mm diameter of bar at a spacing of 200 mm center to center reinforcement it will be. Now I have to find out this reinforcement, what diameter will be, what spacing will be. Just go to this calculation. Okay, one more thing, how much reinforcement finally you have provided? Area of steel provided will equal to AST 113.09 divided by 200 final spacing multiplied by overall width. Total area of reinforcement here it is what provided? 848.18 mm square. Now I want to find out how much percentage of reinforcement is there. So percentage of reinforcement is going to become what? Total area provided divided by 1500 multiplied by overall depth of the foundation slab multiplied by 100. So I am getting 0.1256. Minimum requirement is what? 0.12%. So we are providing more than of the minimum requirement. Hence I am going to say that my provided reinforcement is what? Okay. Now the last reinforcement under the column C2 at the bottom face along the longitudinal direction or along the length of the footing is what? How much movement is there under the column C2? So have a look over this. How much movement is there under the column C2? 150 kilonewton meter. So multiply this value with 1.5. So you are getting factored movement as 225. It is the sagging movement, means the reinforcement will be at the bottom face. The same formula is there. You have to put all the respective values. Only what change will be there? Movement, ultimate movement. Ultimate movement is what? 225 kilonewton meter. Okay. So with all of this, we are getting the value of the area of reinforcement required as 1691.52 mm square. This is what the design requirement. And your minimum requirement is what? 810 mm square. Now compare minimum and design requirement. Design requirement is more. So I am going to provide 12 mm diameter of bar and unit area is 113. Now how much spacing is required? Unit area divided by required area multiplied by width of the foundation. Requirement what we are getting? 100.28 I am going to provide the final spacing as 100 mm center to center. So finally provide 12 mm diameter of bar at a spacing of 100 mm center to center along the length of the footing under the column C2. Okay, so area of steel provided, unit area divided by final spacing multiplied by width, you are getting what? 1696.35 mm square area of reinforcement finally we are going to provide under the column C2 at the bottom face. So percentage of steel available will be provided reinforcement finally, width of the footing, overall depth, you are getting 0.251% of reinforcement you are going to provide, which is greater than of the minimum reinforcement. Here again your provision is what? Okay. So this is about the longitudinal reinforcement under the both of the column as C1 and C2, that will be at the bottom face, and second the reinforcement in between of your C1 and C2 column, that will be at the top because of the hogging movement. So this is the calculation for the reinforcement along the length of the foundation. Now the next is what we need to find out, the reinforcement along the transverse direction or along the width of your foundation. Now after deciding of the reinforcement along the length of the foundation, now we have to find out the how much the reinforcement required in transverse direction, or in another way you can call it as how much the reinforcement required along the width of the footing at its bottom and at its top. So this I want to calculate how much the reinforcement required along the width of the footing. For that I am going to consider the load that is coming from your column C1 and column C2. It is going to be distributed for a width as equal to A plus 2D, where D means at a distance of D from the face of the column. So this is what side of your column in the considered direction. So that is what for the column C1 it is going to become A plus 2D, and for the column C2 this side is going to become A plus this 2D from the column face as D. So this I am going to call it as design strip, and for this width I have to do the calculation. I have to do the calculation along the width of the footing, and for this it is going to become width of this design strip. So very first I want to calculate how much moment is going to be developed at the face of your column as C1, and I have to do the calculation for the C2 also. So first of all we are going to concentrate on the column C1. So here I want to calculate how much the moment is going to be developed at the face of your column C1. Okay, moment I have to calculate here in transverse direction. So for that I need to know how much this projection from the face of the column. How you can calculate that? Very simple, it is 1.5 is the total width minus this side of your column, because our column is square column, 250 by 250 mm is the size of your column. So if you are taking the difference of 1.5 minus 0.25 side of your column divided by 2, so you will get this projection. Okay, the same formula you will get from here. So we are going to do the calculation for the transverse reinforcement for the column first. So projection of the slab in transverse direction beyond the face of column C1. What is the formula? That is what? 1.5 minus 0.25 divided by 2. So we are getting the projection as 0.625. Thereafter, what is the width over which the column load is going to be distributed? It is what? B dash. I am going to represent it by B dash. It is simply what I told you, A plus 2D. Let me show you. It is what? A plus 2D. So with that A plus 2D, if you are going to do the calculation, it is going to become 0.25 plus 2 times. Effective depth is what? 0.392. So width of the design strip is going to become 1.034 meter. So for this width, your column load is going to be distributed. Now I want to calculate the net upward soil pressure under the column C1. The overall upward soil pressure is different. Now I have to calculate net upward soil pressure under the column C1. For that, the load coming from your column C1 is 300 divided by width over which load is going to be distributed multiplied by full width. So this is I am going to call it as what? My design strip. So here upward soil pressure we are getting as 193.42 kilonewton per meter square upward soil pressure. One more thing, here actual width of the design strip we are getting as 1.034. But to make the calculation easy or to understand the thing in well manner, so what I am going to do, I am going to consider 1 meter of design strip as a width. So instead of this width 1.034. I'm going to do the calculation for only 1 meter width. So now we are considering 1 meter wide strip for the design. Here movement at the face of the column is going to become upward swile pressure square of your projection 0.625 square divided by 2. You are getting the moment 37.78 kilonewton meter. You have to multiply this value with 1.5 to have the factored moment. So we are getting 56.68 kilonewton meter per meter width of the design strip. That is the most important thing. Now effective depth in transverse direction. So actually overall depth we are knowing 450 minus your 50 mm is clear cover minus 12 mm. So this is what the diameter of bar at the bottom in longitudinal direction along the length of the footing 12 mm diameter of bar, that is minus half of diameter of transverse reinforcement, that is what 12 mm, that half of that is going to become 6 mm. So I am going to put here as 6 mm. So overall effective depth available in transverse direction is 382 mm. Now area of steel required, same formula is there that we have earlier used with all the values as 0.5 characteristic strength divided by yield strength of your steel Fe415 1 minus square root of 4.6. Ultimate moment is what? How much? 56.68 into 10 raised to 6 divided by characteristic strength again 20 per meter width 1382 effective depth available multiplied by 1000 effective depth. So you are getting the reinforcement required along the transverse direction under the column C1 for a 1 meter width of the design strip. We are getting the demand of the reinforcement as 420.78 mm square per meter. Now area of reinforcement required as minimum as per your codal recommendation. So codal recommendation is what? 0.12% of B into D. Consider width is what? 1000 1 meter width. Overall depth is 450. 540 mm square per meter reinforcement is required. You have to compare your design requirement with your minimum requirement. So we are getting more minimum requirement. That's why we are going to provide this reinforcement. So provide 12 mm diameter of bar with a unit area of 113.09 mm square. Now here spacing required 113.06 divided by total area of reinforcement that we are finalizing to provide and over the 1 meter width. So spacing required as 209.25 mm. So here I am going to decide that I will provide the reinforcement at a spacing of 200 mm center to center. So 12 mm diameter of bar at a spacing of 200 along the width under the column C1 of the footing. Likewise, we need to find out the final area of reinforcement provided. So final area of reinforcement provided you are getting by the formula 113.09 unit area divided by provided spacing finally multiplied by considered width. So you are getting the reinforcement required for 1 meter width of the strip as 565.45 mm square per running meter of the width. Okay. Now percentage of reinforcement provided, area of steel divided by B into D, you are getting the percentage of reinforcement provided as 0.126. Demand is what? Minimum as 0.12%. So we are going to provide more percentage in respect of your minimum requirement. Hence we are going to say that provision is what? Safe. The same calculation we have to do for the column number C2. Have a look over this. Now for the column C2, I want to calculate the bending moment at the face of my column here. How I can calculate the bending moment? So for that I need to have this projection plus I need to have the net upward swile pressure under the column C2. These both things I need to have. Also I need to have this width A plus 2D. A is your side of your column and this side of your column is what? 300. As our column is a square column, both sides are actually 300 mm. Okay, so 300 mm plus 2 times effective depth. So I am going to do this same calculation here also for the column number C2. So here transverse reinforcement under the column C2, projection of the slab in transverse direction beyond the face of your column C2. Actually it is what? C1. It should be C2. Okay, I will correct it. So see 1.5 minus 0.3 divided by 2. So we are getting the projection as 0.6. Now width over which the column load is going to be distributed A plus 2D. So 0.3 plus 2 times the effective depth. We are getting the width of the design strip as 1.084 meter. net upward soil pressure, the load coming from the column C2 is what? 500 kilonewton divided by design strip width multiplied by overall width. See, this is the 1.5 and this is the width we have calculated as 1.084 meter. So upward soil pressure you are getting under the column C2 as 307.5 kilonewton per meter square. Now we are going to consider 1 meter width of your design strip. Okay, so movement at the face of column is going to become net upward soil pressure multiplied by projection 0.6 square divided by 2. So moment you are getting 55.35 kilonewton meter per meter width of the design strip. Actual design strip width is what? 1.084. But I am not going to do the calculation for full width. For this full width, I am going to make the calculation for 1 meter width. Okay, that's why it is needed to write here as per meter width. Okay, thereafter just come down and now movement, ultimate movement is going to become 1.5 multiplied by service movement. You are getting final factored movement as 83.025 kilonewton meter per running meter. Effective depth in transverse direction, against the same formula, you are getting the effective depth as 382 mm. Now area of steel required 0.5 into 20 characteristic strength divided by yield strength of your reinforcement inside bracket 1 minus square root of 1 minus 4.6 your factored movement 83.025 into 10 raised to 6 divided by characteristic strength multiplied by width considered as 1 meter multiplied by 382 is the effective depth available. Now 1000 width multiplied by effective depth. With all of these values, if you are going to do the calculation, you are getting the reinforcement required as 623.38 mm square per running meter. This much area of reinforcement required, I am going to call it as design requirement. Now you have to compare this design requirement with the minimum requirement as usual. So minimum requirement is what? 540 mm square per running meter and design requirement is 623. You have to compare these two. Which one we are getting more? We are getting the design requirement more. So we are going to provide design requirement. So 12 mm diameter of bar, unit area as 113.09 is spacing required over the width. Unit area divided by total area multiplied by considered width, you are getting 181.36 mm spacing required. So here what I am going to decide, under the column C2, here I am going to provide the spacing as 100 mm center to center spacing. If you are providing like 175, if you are providing 150, if you are providing 125, if you are providing 100, so these all are okay. The lower value you have to provide. Okay, so here also I am going to provide, instead of this 181.36, I am going to provide it will be too less. That's why I am going to provide here as a spacing instead of 181, I am going to provide 150 mm center to center. So provide 12 mm diameter of bar at a spacing of 150 mm center to center along the width under the column C2 of the footing. Area of steel provided is going to become a unit area divided by final spacing. How much the final spacing? 150 mm center to center. Now over the 1 meter width, how much finally area of reinforcement provided? So I need to calculate that. So with this 150 mm spacing over the 1 meter width of the foundation, we are getting the reinforcement provided along the width of the footing under the column C2 as 753.7. So it is wrong actually. It is 753.7 mm square per running meter. Now how much the provided percentage of reinforcement is? So here the provided percentage of reinforcement is going to become total finally area of reinforcement provided 753.7 divided by 1000 multiplied by width of the overall depth of your foundation multiplied by 100, you will get the percentage as 0.167. So finally the reinforcement provided under the column C2 in percentage as 0.167. So in this way you have to find out the reinforcement under the column C1 and reinforcement under the column C2 in transverse direction. Now in the last we have to check for the one-way shear to decide that our project depth is safe or not. For that I need to consider the critical section at a distance of D from both of the column as C1 and C2. But here there is some problem with your C1 column. What is that? Try to understand. Suppose this is your combined foundation and this is our column as C1, and we know that from the center of your C1 column up to the edge of the footing, we are having the only the projection as 0.5 meter, and the side of your column is 250. So half of this 250 is going to become what? 125, and this projection overall is what? 500 mm. So 500 minus 125, how much you will get? You will get 375 mm available projection from the face of the column up to the edge of the footing. How much is there from the C1 column? It is 375, and our effective depth is what? 392. So your one-way shear section coming outside of this edge of the foundation, so here your one-way shear check is not possible to perform, right? So same thing here, it is given critical section at a distance of D from the face of the column C1 fall beyond the edge of the footing, hence no check is needed under this column. Now what about column C2? So for the column C2, if you are going to check from the face of your column, this projection is what? It is more than of 392 mm. That's why here we are going to perform the one-way shear check from the face of your column C2. So that's why what is the formula? The formula to find out the shear force, how much the shear force is going to be developed at a distance of D from the face of the column C2. So formula is going to become upward soil pressure multiplied by width of the footing multiplied by projected length beyond D. So if you are going to consider critical section at a distance of D, so how much remaining projected span of the footing is there? This I want to calculate, and the formula is going to become, this projection is what? 1.5 meter minus half of your size of the column. How much it is? 300 mm. Half of that is going to become 0.15. 300 mm means 150, or in meter if you are going to consider 0.3 divided by 2, it is going to become 0.15. So 1.5 minus 0.15 minus this effective depth as 0.392. So same thing is actually given here. You have to multiply this projected length with width of the footing as 1.5 multiplied by upward soil pressure as service upward soil pressure as 88.89 that we have calculated in the start of this problem solution. Okay, so here we are getting the shear force as 127.73 kilonewton service shear force that is going to be developed at a distance of D from the face of your column. I am going to multiply this value with the 1.5 factor, so we are getting the factored shear force as 191.6 kilonewton. Now I want to calculate nominal shear stress tau V, so VU upon BD, put all the values here. 191.6 multiplied into 10 raised to 3 divided by full width multiplied by effective depth 392, you are getting the nominal shear as 0.326 MPa Newton per mm square. This is the nominal shear. I have to compare this nominal shear with the critical shear, critical capacity of the section at this section. How much the critical capacity of your foundation slab? So for that I need to know how much longitudinal percentage of reinforcement available under the column C2 at this section, and that we know that we have already calculated under the column C2 in longitudinal direction. See, longitudinal tensile reinforcement under the column C2 at bottom, how much it is in percentage, that we have calculated already. 0.251% of reinforcement is available there. That's why we are performing this one-way shear at the end. Many of you may think that why we are performing this one-way shear at the end? Because to perform the one-way shear, we need to have the percentage of reinforcement. So without of having the percentage of reinforcement at that particular section, how you can perform the one-way shear check? That's why I am going to do the check against the one-way shear at the end of the problem. So finally, we are having the percentage of reinforcement as 0.251 and characteristic strength of concrete is 20. Now we are going to refer IS 456 2000 clause number 40.4 table number 19. Have a look over the IS code 456. So this code and this table will tell you about how much the critical shear, and this depends on available percentage of reinforcement as well as your grade of concrete. So available percentage of reinforcement is what? 251. Okay, so that is coming in between of 0.25 and 0.5. So I need to know how much critical shear. For 0.25 is 0.36 for M20 grade. For 0.5 it is 0.48. Now our value is 0.251%. So we have to find out the critical shear for 0.251. So go back to your calculation, and here for 0.25, 0.36, for 0.5 it is 0.48, and I just want to do the calculation for 0.251. So here initially there will be what question mark. I want to do the linear interpolation to find out the critical shear for 0.251. But after the linear interpolation, you are getting this value as 0.3604. Right. So nominal shear is 0.326 and critical capacity is what? 0.3604. Means your nominal shear is less than of your critical capacity. Whatever the capacity is there, the action of the loading is less. That is what safe thing. Your capacity is there to carry the whatever the load is going to be developed there. Hence that I am going to say there is no need to provide additional shear reinforcement. Our project depth is safe in one way shear. Now have a look over the final design schedule and details. We are going to provide a footing size as length 6000 mm, as width 1500 mm, and overall depth of the foundation as 450 mm. The reinforcement at the top face of the footing we are going to provide as 16 mm dia at a spacing of 125 mm center to center for the top face. And as we know that between your C1 and C2 column there will be the design requirement of the reinforcement at the top face, but we are going to extend this reinforcement up to the edge 16 mm dia at a spacing of 250 center to center. So at the top face longitudinal reinforcement will be what? 16 mm dia, and for the left part 125 mm center to center, and it is going to be extended as 250 mm center to center, that you can also see in the plan. Here in the plan view of the top face, on the left hand side, here 16 mm dia at a spacing of 125 mm center to center, it is going to be extended with a spacing of 250 center to center. Thereafter we have to provide the reinforcement at the bottom face. So you know that the longitudinal reinforcement or the reinforcement along the length of the footing at the bottom face is required as under the column C2 at the bottom and under the column C1 the design requirement at the bottom. Okay, so this reinforcement we are going to provide under the columns as C1 12 mm dia at a spacing of 200, under the column C1, and under the column C2 we are going to provide 12 mm dia at a spacing of 100 mm center to center. Just come down, have a look over the bottom face. So left longitudinal reinforcement is 12 mm dia, 200 mm spacing center to center. Right side it is what? More reinforcements are required, 12 mm dia at a spacing of 100 mm center to center. For the remaining portion there will be the what? Reinforcement at a spacing of 200 mm center to center, that I am going to call it as extended reinforcement. So here it is what? Given in your schedule, extended reinforcement 12 mm dia at a spacing of 200 mm center to center. This is all for your longitudinal reinforcement, means along the length of your foundation. Now what about the reinforcement about the width of the footing? So along the width of the footing, that is what? Transverse reinforcement at top we are going to provide throughout the span as 12 mm dia at a spacing of 200 mm center to center. Have a look over this. At the top face all the bars having the spacing 200 mm center to center with a 12 mm diameter of bar. Likewise at the bottom face we need to look at the details. So look at the bottom face in detail. So for under the column C1 the transverse reinforcements are 12 mm dia at a spacing of 200 mm center to center, and under the column C2 for 1 meter width, okay, 12 mm dia at a spacing of 150 mm center to center. For rest of the portions the spacing is what? 200 mm center to center for the transverse reinforcements. Hope that you all understood this complete schedule of combined foundation and this complete detail of this combined foundation.
Hello everyone, welcome you all in a new ISO certified live training program, Design of Substructure using CSI Safe, Excel and Manual. In this training program, you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real life project, we will cover the raft foundation. And in the fourth real life project, there will be the coverage of pile and pile cap design of basement wall. And at the end of this training program, we will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by experts recording of every session, can interact with expert anytime, exposure to real practice, ISO certification of training. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next.